All right, we are going to start talking about Chapter 7. Chapter 7 collectively is referred to as analytical trigonometry, which is, when we do something by hand, when we manipulate a problem, go through a problem by hand, not using technology, for the most part, those types of things are referred to as analytical, okay? We're going to do a lot of substitution, okay? A lot of rewriting a phrase, an algebraic phrase, into something that is simpler, okay? We did a little bit of this in Chapter 5. Remember when I said take sine and rewrite it in terms of cosine? Or take tangent and rewrite it in terms of sine, or something like that. That was a brief introduction to analytical trigonometry. If we run through real quick, so these are the identities. Hopefully these are fundamental identities that we already know. Okay, but I want to run through, if we already know those, and we're talking about it a little bit more today, those help us build these, which are new formulas. Okay, and what this allows us to do is say, if I don't know what the sine of 75 is from the unit circle, I can actually break 75 down to 30 plus 45, right? Do we know 30 and 45 off the unit circle? You know, sine value of 30, sine value of 45? So then I can use this formula here to help me actually find the sine of 75. All right? But without these here, and an understanding of the distance formula, this here cannot be constructed. Okay, so these are called our addition and subtraction formulas. We have something called double angle formulas. Okay, this rule here is exactly the same thing as this rule here, but the t is the same thing as s, and I get sine s cosine s plus cosine s sine s, and then we can rewrite it then as this. We get a double angle formula. Okay, we got those for sine, cosine, tangent. Then we'll have something called lowering powers. We have half angle formula. So if I know what 45 degrees is off the unit circle, this formula will allow me to find what the sine, cosine, and tangent of 22.5 would be. Okay. We have product the sum formulas. We have sum the product formulas. All right, so we've got a lot of these formulas that are, and then we get into our equations, which those formulas are then used within our equations. But all of that stuff is based off our knowledge of this blue box right here. Okay, if we have a really good understanding of that blue box, we can generate those other formulas. Not saying easily, but we can generate them. Okay. And then hopefully utilize them in a meaningful way. But this is called analytical trigonometry. One thing that I think is important as we go through this, if you miss something, if you miss a day, okay, or if you come to class and are worried about getting the homework done while I'm instructing, okay, you are going to get lost, and it's going to be very, 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 very hard for you to get yourself unlost. Okay. In the past, and you guys remember doing proofs in geometry? Okay. Do you remember the difficulty that some of us realized with proofs in geometry? Okay. You're going to realize that difficulty again. Okay. Some of these are what we call trigonometric proofs. Okay. Try to make it as easy as I can in regards to kind of leading you down the right path, giving you as much instruction in techniques and tools that I possibly can. But at the same time, if you don't accept those, it's going to be hard. Okay. In the past, I've had students with this chapter. They get it day one. Okay, and it creates no issues for them. Okay. But then I've had students that have to bust their butt and work very diligently to make sense of it. Kind of like what students had to do with proofs. With proofs, some people got that day one, never had an issue. Some people still can't do them. Okay, so I don't want to say that this stuff is going to be hard. I don't want to scare you, but at the same time, I kind of want to scare you. okay? Because I want to make sure that you understand that if we don't commit to this, it's going to be an agonizing 5 or 6 weeks. Okay. First thing we want to talk about is what an identity is. We talked about this in chapter 5. We talked about this the first day of college algebra. An identity is an algebraic expression that is always true regardless of the input value that you use. Okay. So if I look at that first one, that's a linear identity. Okay. So if I were to graph these things, what we mean by that they're always true means that the graph of the left-hand side coincides or 100% overlaps the graph of the thing on the right-hand side. Okay? And after doing a little bit of maybe algebraic manipulation, you can see that the left-hand side turns into the right-hand side. So if I take that first one and multiply that through with the 2, right? Do I get 2x minus 6? Which is the right-hand side, right? So I get the left-hand side to look exactly like the right-hand side. That's an identity. Okay? We did binomial expansion last year with Pascal's triangle. This is one of, you learned this in Algebra 1, but this is one of those rules. Okay? X plus 1 squared turns into x. You square the first thing, square the last thing, multiply these two things together and double it, right? And that gives you a middle term. That's an identity, because no matter what you put in for here for x, if you put the same thing over here, they both evaluate to the same thing. Okay? So that's a linear identity. Here's a quadratic identity. This here is a trigonometric identity. Okay? And that trigonometric identity, remember, this is where this comes from. We call it a Pythagorean identity. But every circle that we've ever come across, okay, you should have talked about circles equations in Algebra 2. But every circle you ever come across is that equation, where h and k is the location of the center. That should be k. Every h and k is the center of the circle, and r is the radius. When we deal with the unit circle, h is 0, k is 0, right? So it goes to x squared plus y squared. What's the radius on the unit circle? 1. Okay? Now, if you go on the unit circle, every one of these ordered pairs, the x value is the what? Cosine. So that x replaced with cosine. And it's cosine of t, or theta. I'll just put theta here. And then every y value is sine. So that's where that identity comes from. That's why that's true. Okay? So cosine squared plus sine squared equals 1. Now, they're going to bounce back between using x as the input, using theta, using t. Doesn't matter what your variable is. The relationship's always the same. In graphing things, we can say, okay, well, if that's true, then I should be able to take cosine squared x plus sine squared x. Does that equal the same thing as y equals 1? Graphs are the same, right? Okay. In this image, hopefully, demonstrates that no matter what x value you plug in, you put 5 here, put 5 there, put 5 there, you get 1. Okay. Put that number there. Oh. And then 1, 2, 3, 4, 5, 6, 7. Okay. Same exact number. Get back 1, right? Does not matter my input. I'm always going to get back 1. Okay. So that's a trigonometric identity. These are reciprocal identities. Okay. Now they're only showing them in one direction. Okay. And so what I mean by that is they say that cosecant is 1 over sine, right? So sine is 1 over cosecant. And the way we generate that, and this is a very small practice of what we're going to do overall in this chapter. If I have cosecant is equal to 1 over sine, algebraically, is it okay to multiply this side by sine of x multiply this side by sine of x. Okay? So then I would have sine of x, cosecant of x is equal to 1. Thank you. And then how do I solve for sine? I would divide both sides by cosecant, right? So that is another way that we can identify the reciprocal relationship between cosecant and sine. Okay? Most textbooks only show it one direction, okay, but reciprocity, okay, being reciprocals is a two-way street. Okay? So we have the same thing for secant and cosine. We have the same thing for cotangent and tangent. Then we also have, I usually refer to these, I don't usually call this a reciprocal identity. I call those quotient identities because that's what we're getting there, right? Tangent turns into the quotient of sine over cosine. But they're referring to them as reciprocal identities if we look at them as look at these two. I hate when it does this. So, there we go. When we look at these two collectively, tangent and cotangent are reciprocals of one another, and you can see that that is then the reciprocal of that, right? Got our Pythagorean identities. Yeah, there's three of them. There's actually more than three of them, but those are the three basic ones, okay? You can, because of how we manipulate equations, you know, I could solve this one for tangent squared by subtracting 1, right? And that'd be a new identity. I can subtract cotangent squared from both sides here, and it give me a new identity. I can subtract 1 from both sides here, and it give me a new identity, okay? But these are the three that we utilize the most. And these two, and I told you this in chapter 5, those are, I think, a struggle for people to remember. So I want to show you real quick, just to jog our memory again of how we get those. If I have sine squared x plus cosine squared x equals 1, that is an identity, okay? To get other identities, we make substitutions, or we conduct equation rules, or we make substitutions, okay? Really do the algebra that we've been spending 3 years on trying to learn, okay? I'm going to go through here, and I'm going to divide everything by the same amount. And I can do that, right? And I start with an equation. As long as I divide everything by the same thing, I'm going to be fine. I'm going to divide everything by cosine squared. Okay, now you would not go this detailed eventually, but sine squared over cosine squared, that leads to sine of x times sine of x all over cosine x times cosine x. Does everybody agree with that? Okay, so I'm just going to color code these so that you can see what matched up. Would you guys agree that this one here is cosine x times cosine x all over cosine x times cosine x? Got that plus sign there, so I'll color that one green. And this one on the right, would you guys agree that that's 1 over cosine x times 1 over cosine x? Does that still multiply together and give me 1 over cosine squared? Okay. Now, eventually, my hope is that we don't do this row, okay, of work. But the reason I did that is, what is sine divided by cosine? Tangent. Okay, and because this is all being multiplied together right here in this yellow fraction, you can use the commutative property as you see fit so that you recognize relationships like that, right? So there's a tangent. What's this one? Also tangent, right? Now if I look at this one, what's that going to turn into? 1. What's that going to turn into? 1. So 1 times 1 is 1. What's that turn into? That's secant. And what's that turn into? Secant, and they're multiplied together. So I get, what's tangent times tangent? Tangent squared. And secant times secant? Secant squared. Okay? Now my hope is eventually we can actually go from, once we realize that we have to divide by cosine squared, then we go straight to that. And the reason we can do that is that as long as these powers are the same, sine divided by cosine is always tangent, then to whatever that power is. So if it was sine cubed or cosine cubed, it'd be tangent cubed. Does that make sense? Okay. Same thing here. Okay, those cancel out completely, giving you just 1. And then 1 over cosine squared would be secant squared. 1 over cosine cubed would be secant cubed, because of that 1 being able to be rewritten as a product of 1s as many times as we need to. So that is where this identity right here is generated. Okay. Say it again. You could probably generate, so you're saying how I generate that one? Yeah, you could use reciprocal identities. What I think is easier than the algebra that would be involved in that, and maybe at some point we will do that algebra, is to take this thing that we started with here, sine squared plus cosine squared equals 1. Instead of dividing by cosine squared, what can I go through and divide by? Sine squared. If I divide everything by sine squared, the same practice will generate that. But I would agree that reciprocals of this would eventually lead to that. Here's our even odd identities. Those are things we were, hopefully remember from the last chapter. And those are just coming off the symmetry of the unit circle, right? So if I want to go sine of negative x, I'm going to travel clockwise, okay? And we'll find my y value. That y value is going to be the opposite of the y value that if I would have traveled the same x but in a counterclockwise direction. Okay? So basically what they're saying there is that your y value in the bottom half plane of your unit circle is going to be the opposite of the y value in the top half plane of your unit circle, which hopefully makes sense, right? Third and fourth quadrant are opposite of the first and second quadrant in regards to y values. Okay. The cosine one says that basically the fourth quadrant and first quadrant for x values are the same, and the third quadrant and the fourth quadrant of x values are the same. Okay. And then the tangent has really the same relationship that sine had. Okay. These are our cofunction identities. Okay, these become really nice because if they provide me a problem, an equation that has this in it, it's going to be so much easier to replace it with what it's equal to. Because now the argument, the x part, or the pi over 2 minus x part, is so simpler when it's just x, right? Okay. We worked with these graphically. We did transformations, and we showed how with graphs, if we take the sine function, the cosine function, we can take one of them and move it pi or 2 or 90 degrees left and right, correct, to become the other one. And then we worked through the usage of our even odd identities in tandem with that transformation to actually get this. I think if we went back to section 6.4, we would see the notes that allowed us to develop that rule right there. Okay, but if you look at this, and we've got, when we talk about trigonometry, we've got 3 words. We got sine, we got secant, and we got tangent. And if I add the prefix co on top of those, or in front of those, sine turns into cosine, tangent turns into cotangent, and secant turns into cosecant, right? Okay, and those are the ones, those work together in terms of being complementary. If I add those arguments, pi over 2 minus x, and x, and each one of those, what's pi over 2 minus x plus x? Pi over 2, right? The x's cancel out, right? And what's pi over 2 in regards to degrees? 90 degrees. And 90 degrees, 2 angles added together, you get 90 degrees. They are complementary, which is this co-idea. Okay? Understand, cofunction does not mean reciprocal, right? Sine and cosine are not reciprocal. Secant and cosecant are not reciprocal. Are tangent and cotangent reciprocal? Yes. So that's kind of the oddball. Tangents and cotangents, they can always go together. They are reciprocal and they are cofunctions. The other ones are not. Okay? Yes. So what's going to happen here is that we are going to be asked questions that allow us to manipulate the presented expression and replace parts of it with these relationships. Okay? What stinks, and it's just like when we did geometric proofs, and even if you do any other mathematical proof, no proof or starting question tells you where to go. Doesn't tell you how to start. All right, so hopefully give you some tools and techniques to assist with that. You guys remember, and just kind of make a comparison, a little bit of a comparison to what we're going to do here and what we have done. Probably the second, third week of Algebra 1, we gave you something like this, 2xy minus 3zw. And we asked you to evaluate that when x was 3, z was 2, w is 5, and y is 12. You could substitute those things in, right, and evaluate that. Similar thing's going to happen here. I'm not going to give you values for certain things to substitute, but you're going to try to use our identities to try to substitute. So in a problem, you might see where it says tangent. Well, you're going to replace that with an identity of sine over cosine. Does that make sense? Okay. And if you don't know those identities in that blue box, it's going to be mighty hard to make the appropriate substitutions. Okay. Obviously, there's some trigonometric concepts here that we need to learn and that we're focusing on. But I think the greatest result that you're going to see from this chapter, because to be honest with you, are you going to solve trigonometric equations very often in your life? Probably not. Okay. Maybe you go to physics and maybe you can use some of this in your sine wave stuff, your cosine wave, your light waves, all that stuff. You can probably use this a little bit there. But in everyday, practical, applicable use, probably not. Okay? But you are going to increase your algebra skills in the next 4 to 5 weeks greater than they've ever been increased in a 4 to 5 week ever. Does that make sense? As long as you let frustration be a motivator. Okay? Because every one of you is going to get frustrated at some point with this stuff. I still get frustrated with it. Okay, I've been doing it for 20 years. But if you let it motivate you, you will get better. Okay? There's no way that we're going to see enough examples in class to become experts at this. Okay? But if you use my website, you're going to find a lot more examples. You're going to find links to other videos on YouTube and stuff like that you can go back to and use as well. Okay, I already laid out that we've got 38 days left, and 12 of them are 2-hour delays, 3-hour delays. Okay, so we're going to be running short on time. So you might have to do. I'm not going to say might. You will have to do, if you want to get really good at this, some stuff on the side. Yes. We got this chapter, parts of chapter 8 and parts of chapter 9. So we're not too far from the end. But to simplify this expression, okay? Now, what kind of stinks, and it's just like any other Algebra 1, Algebra 2 problem that says simplify, that means get it down as far as you can. Get down to an equivalent version of itself as far as you can. Okay? Usually it means you only want like one trig function left over. Sometimes they will specify. They'll say express the following in terms of only sine, or in terms of sine and cosine, or something like that. They might add extra details to the directions to tell you how far to go. But if they don't, the assumption is you go as far as what is possible. Okay. So this one, actually, let's do number 2 first, because number 2 is much simpler. It gives you an idea of what we need to do so we can attack number 1 maybe a little bit more efficiently. All right, so kind of rule of thumb type techniques or steps to take when we're doing these is to first look at the entire expression and look for powers that are bigger than 1, okay? Because if I have powers that are things that are squared or cubed or fourth, the first thing to realize that if it's a power that is of 3, of 4, of 5, then those can all be dwindled down to powers of 2, okay? And we like powers of 2 on our sines and our cosines and our tangents and our secants and our cotangents and our cosecants, because those are going to allow you to make Pythagorean identity substitutions. They're going to allow you to attack the tangent squared plus 1 equals secant squared. They're going to allow you to look at cotangent squared plus 1 equals cosecant squared, or cosine squared plus sine squared equals 1. Does that make sense? Okay. So if you have powers that are squared, that should switch a light bulb off real quick for you and allow you to make a quick substitution. Okay. If you cannot do that, okay, the next thing you want to do is rewrite everything that you see in your problem in regards to sine and cosine. So if I have a tangent in there, I don't want tangent to be left in there. I want to get rid of it. Put it in sine and cosine. If I see secant, I don't want secant in there. I'm going to write it as 1 over cosine. Does that make sense? If you do that, okay, what that allows you to end up developing is a expression that you can manipulate solely on algebraic skills. Okay? So if you're somebody that says, I'm a master, I'm an algebra ninja, then changing everything to sine and cosine, you will have no problems with any of these. Okay? But you have to be able to recognize what the algebra is telling you to do. Okay? Because as I make a substitution, directions don't pop up miraculously, right? Okay? So I have to know what the implied algebra is telling me to do for my remaining procedures. So, starting with question number 2 here. There's no powers of 2, right? So we're going to go through, we're going to rewrite everything so that we only see sine and cosine. One issue that we usually get with some of this stuff is just our structure, how we write things. When I write, like a lot, I deliberately wrote that so that this denominator was showing up kind of lower than this one. But a lot of times I'll write this as 4 cosine t, and then I'll just say sine t, cosine t. So you don't necessarily see it. That's they kind of look, they're more aligned there. Does that make sense? But I want to write it deliberately here so you can see that is a fraction times a fraction. Does that make sense? And that's what I'm talking about. You need to be able to see and recognize the implied algebra. The implied algebra here is that you're going to multiply this fraction times that fraction, right? And yes, so I can cancel the cosines. Now you would probably just go cancel, cancel, right? But I want to demonstrate, because I get a lot of times as we progress through this, people cancel stuff that should never ever be canceled. Okay? I want to show you why the cancellation occurs. Can I use the commutative property to rewrite this as 4 sine of t cosine of t over cosine of t? Is that okay? Okay. Now, because this is a product up here, and this is a product down here. Now, you don't recognize that this is I'm going to be kind of goofy with this. Can I multiply this by 1 and still have that product? I'm going to multiply it by another 1 as well. And the reason for that is that you can now say, if this is a product of 3 numbers up top, a product of 3 numbers on the bottom, that means this is a product of 3 ratios. 4 over 1 times sine of t over 1 times cosine of t over cosine of t. Does that make sense? Why were these able to cancel like they did? Because that is a factor of 1. That turns into 1. And if I multiply everything that's left over, it's 4 sine of t, right? Does that make sense? So, but a lot of people will cancel that right away, and you're left with 4 sine of t. And that's the way I'm going to do it from here on out. But I want you to understand when you're allowed to cancel. You're only allowed to cancel when you have a factor on top and a factor on the bottom inside the exact same fraction, right? Because I get this a lot. Let's say that we had something like 4 sine of t over 1 plus 5 sine of t right there. Number one thing I get people to do, boom, boom, cancel them. Why can't I cancel those? Are they in the same fraction? No, these are a sum, right? Okay. Another thing that I like to be able to do is take my calculator, and we'll see this especially on the next question, and I start with the problem. I start with 4 cosine of x tangent of x. Now I'm going to use x so it graphs it, and that's the graph. Then I'm going to say, okay, well, I tried this. I went 4 cosine of x, and I wrote it as sine of x over cosine of x. Is that okay? Why is it okay? Yeah, and graphically, are we seeing we'll get the same result? Yeah. Okay, so I'm saying right now, this is an identity. That thing right there is always that thing right there. It's an identity. It's not a useful identity in which we're going to remember for the next problem. Okay, sine squared plus cosine squared equals 1. That's an identity that's useful for every problem that we're probably going to see. Okay, right, maybe 75% of the problems that we're going to see. This is not an identity that's going to be useful in any problem that we see beyond this one. Okay, so we don't commit it to memory. And then we thought, well, the answer, once those cancel, once the cosines cancel, we get 4 sine of x. Is that confirmed then that this does simplify to that? Okay, and this isn't simplest form because I can't change sine to anything. Okay, I could maybe go 4 sine or cosine of like pi over 2 minus x. That's the same thing using one of our identities, but does that look simpler than that? No. Okay, so this is the one we're going to stick with. Is that okay with everybody? Okay. Again, we could do this. We could put a negative there, and then put a negative there, and say, well, that's the same thing, but is that simpler than 4 sine of x? No. We want the most simplistic argument we could possibly get, and the hope is that that is positive. Okay. And then we want the most simplistic trig identity left over, or trig function left over. All right, so the next one, I'm going to go to the side. I don't think I gave myself enough room to really show the progression of cosine t, tangent t, sine t. So cosine t plus tangent t sine of t. Okay. As you do these, and some of these you make one substitution, you're done. Some you make 2, some you make 3, some you make 15. Remember doing algebra or geometric proofs, and some were like 3 steps, 4 steps. Some were 15, 17, 18 steps. Okay. And the problem doesn't dictate. I can't look at this and say, oh, I'm only going to have one substitution. Okay. Some of the most difficult looking problems that you see turn out to sometimes be the most easiest ones to work with. Okay, so don't let the difficulty of them deter the original format of them deter you. So going off of our guidelines a little bit, we're looking for powers of 2. We don't have any of those. So then we'll change things to sine and cosine, right? So that right there is going to change to what? Yep, sine over cosine. So I'm going to rewrite this. So I'm going to say equals, and we'll come down here and actually do the work. So I'll have cosine of t plus sine of t cosine of t times sine of t over 1. Good. And this is where I was talking. Once you have it in terms of sine and cosine, then you rely on your algebra. And if it wants you to simplify, if I had, let's say that cosine t just represents a number when I know what t is, right? So I have a number plus a fraction times a fraction. Well, the algebra tells me if I want to simplify that, I need to start merging fractions, right? So I think it maybe makes sense in order to merge, because basically I'm going to take that fraction there and that fraction there and add them together eventually, right? Wouldn't it make sense to take this fraction on the right and make it one fraction? Okay. So cosine t is going to be left alone. What does this turn into? Sine squared t over cosine t. Okay. Now there's a substitution right there that can happen. Sine of t squared or sine squared t. You can make a substitution there. Okay. My suggestion though is to continue working through the algebra. Make the substitutions later. Okay, because it'll just be easier for you and less messy. So now, what does the algebra tell you? You have a number or a fraction plus another fraction. I want to add those together, so I need a common denominator. What's my common denominator going to be? Cosine of t. So what I like to do is just say, okay, if I'm going to add these together, they're going to have the cosine of t as a denominator. So what do I need to multiply this one by? Yeah, I need to go cosine t there and cosine of t there, right? What did I really multiply by? 1. So did it change this amount? No. So I'd have cosine squared t, right? Here, do I need to do anything? So that's going to leave me with sine squared t, right? Now that you have a common denominator, what can you do? Add them together. So I get cosine squared t plus sine squared t over cosine t. Recognize anything? That's 1. So replace that with 1 over cosine t then. And what's that end up changing to? Secant of t. So we started with cosine t plus tangent t sine t, right? That's what we started with? And it turned into this, right? That's an identity. You want to commit that to memory? That's 100% fine. But it's going to chew up memory, and you're never going to use that again. Okay? Because basically the identities that we learn, or we commit to memory, the reason we do that is because of how prevalent they are later on. That one, you're never going to see, I'm not going to say never, but it's likely that you will not see in a problem later on, cosine t plus tangent t sine t. And then you say, oh, I need to replace that with secant t right off the bat. Okay? You don't see that expression enough to memorize it. Okay? Now, as we're going through this, I said we could have made the substitution right here of sine t or sine squared t. So let's see if, because I like to show alternative pathways. Because your neighbor might do one of these differently. You remember geometric proofs and steps, ordering of steps required an understanding of dependence and independence. Same thing happens here. So I could rewrite, so this was cosine t plus sine squared t over cosine t. We could have at that juncture replace sine squared t. Okay, now, if I have sine squared plus cosine squared equals 1, that's my Pythagorean identity. Then sine squared would be 1 minus cosine squared, right? So I'm going to replace that thing right there with 1 minus cosine squared t all over cosine t. Okay, still going to need what? So I'm going to add these together. Still need a common denominator. So I'm going to rewrite this as, so this will be cosine squared t over cosine t when I multiply that by cosine over cosine. Plus then 1 minus cosine squared t over cosine t. Yeah, so when I add these together, that and that cancel each other out. Does it still leave you with 1 over cosine? Okay, so you have freedom when you see substitutions to make them when you want to. Okay? And much like geometric proofs, you might come across a problem where you start working and you kind of get in like a loop where you just keep making things more and more difficult looking. Okay? If that happens, you're not realizing this is getting simpler and simpler and simpler, or that you're getting anywhere with it, you might want to stop and redirect your attention somewhere else within that problem. Okay? Make different substitutions. Again, there are a lot of substitutions here that we made, so it makes sense, I think, to grab, especially once you're done. If I want to go cosine x plus tangent x sine x, it doesn't know. It wants when it does that, I think it wants the multiplication. Yeah. So let's put multiplication in there. Maybe it wants the print. There we go. I don't know why tangent has to have the parentheses around the argument, but sine and cosine don't. But that's what we get. And when we were done, get the same thing. Okay, so that's an identity. And if I wasn't sure about some of my intermediate steps, maybe at one point I wasn't sure, does cosine of x really equal sine squared of x over cosine of x? And it does, right? Same graph. Or if I was unsure, and because my neighbor did something different, my neighbor said they went cosine of x plus, and then they went 1 minus cosine squared x, but they did that. Oh, wrong button. Over cosine of x. Were either of us wrong? No. Okay. So you can use you can use your TIA 384, but typing this stuff in on TIA 384 is very bad idea. Use Desmos to see if the steps you've made are appropriate or not. See, you have no homework tonight.